Okay. Who can tell me the difference between an elastic collision and an inelastic?
Elastic bounces back and elastic and travels alongside and piggies on.
Bounces off. It doesn't necessarily back.
It just off.
It's just off. They can both actually, you hit pool balls. Sometimes the cue ball will continue in the same direction you hit it, right? Sometimes you can make it come back.
Hey guys, thanks for the card. It was great. How you
Happy
doing?
birthday.
Thank you. Yeah, I know, 70. You have to celebrate 70, isn't it?
Yes, you do.
70 is pretty big, yeah. It's a milestone. Anyway, hope you guys are doing great. Yeah,
This is a good class.
so fun. Thanks, Aaron.
Yep.
Yeah, another one of those sheets. So I think on this.
Yes, hold on. Yes. Yep. Um, yeah.
So no, in that ratio. Like, so if you wanna do once a week, somewhere else, I think, you know, and. And here's a lesson. Oh, it's then movie.
That's one thing you know.
Okay. Can I get everybody's presents back here? So we've got our elastic and our inelastic. What did we learn about momentum when we have somebody release things, a shot put off a skateboard yesterday?
Pushes you back.
Well, it's conserved. It's the same before as after for my system. Okay, when I'm talking about a system, I'm talking about multiple objects, right? And Noah on the skateboard with the shot put was at zero momentum before he threw it, right? Then the shot put had positive momentum going forward, and Noah had negative momentum as he went backwards. The positive plus negative equaled zero. Okay? So to put that in perspective, momentum before equals momentum after. And we'll often see it written like this: P1 initial plus P2, remember P is momentum, equals P1 final plus P2 final. Well, we know that momentum is mass times velocity, right? So for an elastic collision, we can say mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 velocity 1. I wrote that too low. That should not be a subscript. Velocity 1 final plus mass 2 velocity 2 final. That kind of makes sense. I've taken the two initial momentums and they equal the two final momentums. Well, with an inelastic collision, what do we know about the two objects? This, what do we know about the two objects with an inelastic collision? They stick together, so essentially I have one object of mass, the combined mass of adding the two masses together. Does that kind of make sense? So, problem number 1 on here. We have two train cars. They collide and stick together. Train cars are the classic example of an inelastic collision. Okay? And if you look at them, it says what will be the resultant velocity? So we always start by writing our knowns and unknowns. What will be the resultant velocity is my unknown. If you look at the diagram, it tells you mass 1 is 10 tons, mass 2 is 30 tons. So boxcar 2 is more loaded than boxcar 1. Velocity 1 initial is 4 meters per second. Velocity 2 initial is 0. So to solve the equation, I just start filling things in. 10 times 4 plus 30 times 0 equals 10 plus 30 times velocity final. Ten times 4 is 40 plus 30 times 0 is 0. What's my final velocity? 1. That was pretty easy, wasn't it? Okay, that was problem 1. This is going to be problem 12 over here. And I'm doing this because there's a lot in between that are really pretty easy. Problem 12 says during a goal line stand, we're talking about football. Not enough of you know enough things about football, so time to learn what a goal line stand is. The defense is trying to keep the offense from scoring from very close in. No, we're going to do this football problem. During a goal line stand, a 75-kilogram fullback moving eastward with a speed of 10 meters per second.
Does direction matter?
Does direction matter? Did direction matter yesterday with the shot put in the skateboard?
Oh.
Yes, it did.
Oh, yeah.
Otherwise, we would have went from 0 to something. Because it had a positive going forward with the shot put, negative going backwards. So direction is going to matter. One of them has to have a negative sign. So my fullback is met by my 100-kilogram lineman. And these are more like high school football players. Going 4 meters per second west. Oh, it's not velocity 2 final, it's velocity 2 initial. So it should be a negative 4. They collide and stick together. That means I'm dealing with inelastic, so I only have one velocity final. Okay. I'm not giving you an elastic example because it's the same thing, you just have to use the other equation. This one, the key part though is that negative on the 4. It really doesn't matter which one you called negative for the velocity as long as you call one of them negative when they're in opposite directions. Okay? Opposite directions mean one must be negative. So, um, let's plug it into the equation. I suppose I should just put the values in, huh? I'm running out of space, so I'm just going to add the 75 and the 100 together and call it 175. 75 times 10 is 750 minus 400 is 350 equals 175 times velocity final. Velocity final equals 2 meters per second. Which way are they going? The direction of the running back or the defensive lineman? The running back. They're probably scoring a touchdown.
Also to pull back.
To run through people? Yeah, that's what he's supposed to do. That's the goal. Okay, does that make sense? This is not that hard. The conservation of energy is not that hard. You guys have the rest of the class to work on this. Mm-hmm.